can also access it.
Okay. Hey guys, welcome to the Bible review. Yeah. Guys, look at it this way. You're stressed now. I get it. Finals suck. 5 sucks.
Nice.
But raise your hand if this is the last 105 class or chemistry class you have to take. Okay, that's like half of you.
Oh,
The other half,
he used to.
welcome to hell. Just kidding. It's not that bad. It's not that bad. It actually gets easier. It actually gets easier. So yeah, it gets easier after 1 to 5. It really does.
Don't give me sense of fault.
Okay, sweet. Review. Okay, so the final exam, it's open all finals week, I think. Is that true? Does anyone know?
I think so.
Yeah, okay, it's open all finals week. It's gonna be in the RB, I heard. Is that true?
Yes.
So, all finals week in the RB, it's gonna be all multiple choice, so there's no free response. So it should be easier for you guys. It'd be easier than the midterms because there's no free response. Unless you like the free response. So your final exam score, you can actually replace your lowest midterm score if you do better on a final than one of your midterms. So it's actually it can come in clutch.
It's like you saying.
So that's good. Yeah. Yes. Okay, for study materials for this exam, it seems like a lot, but you've got a lot of materials, okay? You have the final exam study guide. Actually, this review is like super heavily based off the final exam study guide. Almost every slide is one of the points with an X on it. So on the final exam study guide, if you guys download it, you have lots of points, but only some of them have a bold X by it. The points with a bold X are points that have a question based on. Okay, so we're gonna go all the slides. Basically, there's questions based on. Okay. So the final exam study guide is pretty helpful. You could look at past recitation sets if you want to. It's good practice. There's a unit 4 practice exam. So just this last stuff that we went over can be really confusing, like entropy and enthalpy and Gibbs free energy and spontaneity and I don't know, a lot of stuff. There's a practice exam on that if you want to practice. We've got lots of YouTube materials. There's Khan Academy, other stuff. You've got lecture slides and notes. We have stuff on that. Tech note, yes. You want? Okay. Any questions on that, on the exam, before we go over the material? Yes.
How many questions are there?
I think there's 50, but I'm not super sure. Okay. So go and expect 50. If there's not, don't let me down. Okay. Sweet.
The weekend plans are canceled now.
That's us. Okay, unit 1. This is where we started. Okay, so we started talking talking about chemical versus physical processes. Okay, so something you should be able to do is you should be able to distinguish between physical and chemical properties, physical processes, and chemical reactions. So if you have like a question and it's going to say, is wood burning a physical change or a chemical change? You should be able to know that wood burning, because the wood is changing identity with oxygen and everything, it's a chemical change, right? But if you have like something like ice melting, physical change, right? Pretty simple. Any questions? Okay. Next, we talked about the laws of multiple proportions and the law of definite proportion. We also talked about the law of conservation of mass, but that was pretty big, right? Nothing stays, can't be created or destroyed. So the law of definite proportions is just saying that all samples of pure compounds contain the same elements in the same proportion by mass. So if you have water in China and water in the United States, it's the same water, right? It's H2O. No matter where you go, it's H2O. You have a drop, you have a bucket, it's H2O, right? There's 2 H's and 1 O. The law of multiple proportions is saying that every compound in existence, 2 elements can combine, but they always combine in small whole number ratios, right? And it was that they started to realize that atoms exist. Okay, does that make sense? Does that explanation make sense? Who's got questions? Okay, yes.
Would you you give us an example of that?
An example of law of multiple proportions?
Yeah.
So, yeah, you can have hydrogen atoms. You can have hydrogen atoms, and you can have oxygen. Okay? Hydrogen and oxygen, they didn't, let's say back in the day, we didn't know what atoms were. But somehow we were able to analyze a compound by mass of elements. I don't know, shut up. Okay, so water, right? They had water, okay? And they were able to weigh it. It was like 18 grams per minute. Okay, so they had 18 grams in it. They also had another compound. Let's call it hydrogen peroxide, H2O2. I don't want to do the math. 18 plus 16 is 34. 34. Okay. They had the masses of these two things. So this is just showing that atoms can combine, but it's always going to be in small whole number ratios, right? It's never going to be like, oh, 0.342, you know what I mean? So we're going to use small numbers. And that's just what the law of multiple proportions would say, is that these atoms always combine with the numbers, okay? Does that make sense? Clear up a little bit? Okay, move on. So the next thing you should be able to do is you should be able to tell if data is accurate or if it's precise, or if it's both, or if it's neither. Okay, hopefully this diagram helps a little bit with reminding you what's accuracy and what's precision. Precision is if we're all together. Accuracy is if it's like close. Yeah.
So what's the threshold for accurate? I remember I got a question on it, yes, because I didn't know what the number was.
I would say if it's 5% off, you know what I mean? If it's like off by a margin of, then it's not.
Right, I think it was less.
Was it less than that? Was it 1%?
I don't remember. I just remember I thought it was 5%. They got
It's not 5%.
I always went by 5%. I think. Did you say anything in lectures? What?
the capability.
Okay, I don't know. I don't know that one. I would just go by gut. I always heard 5%, but I guess it's not 5%.
That's what I thought too.
If someone wants to figure it out and yell it to the class, that'd be. Any other questions? Sorry, I couldn't answer that one. Okay, this is just something that you can memorize. And you should be able to describe the contributions of Dalton, Thomson, Millikan, and Curie to our understanding of atoms. So what they contributed, what their experiments were, and what helped us learn about atoms. Okay, and honestly, this is just something you should memorize. Start on some flashcards, be able to just say, have someone say Curie, but we should be able to say she figured out like her experiment was like the radioactivity, and she figured out just about atoms. It's kind of that from all of those guys. I remember, I think I can tell you this. Mine was online. Yours isn't going to be online, but mine was online. My final, and I remember the question. It was like match the following, and it had like A, B, C, D, E, F, and it had like a bunch of scientists. Then it had a bunch of experiments that they did. Okay, so you should be able to match the scientists with their experiments, what they found out. Yeah, honestly, just kind of memorize this. It kind of sucks, right? No one wants to hear memorize this. But honestly, it'd just be easier. Okay. Sweet. Any questions? Yep. Sweet. And then we talked about natural abundances and average atomic masses. So on the periodic table, the masses that you see, for example, carbon, is 12.011 is the average atomic mass of carbon. What that means is just you take all the natural abundances of all the isotopes, and it's just the average of all the masses of the isotopes. Okay. So this is the equation to find the average atomic mass. Yeah, pretty simple. Any questions? Okay. With this, we can also calculate natural abundances. Okay, so I've got a practice question coming up now. Okay. So ready, set, go. I'll give you a couple minutes to work on this. Just raise your hand if you have questions. I can come around.
Yeah, that'd be great.
Yes, you are.
Yeah, I think that was 31 seconds. How do you guys feel on this one? Good? Okay, what did you guys get for the natural abundance of silver 107? Yeah, even.
51.8%.
51.8%. Did everyone get that? 51.1%, or sorry, 58.1?
51.8.
51.8, sorry. Okay. Solid. We need to go, who wants to go over that one? Pretty good about it? Go over it? Okay, let's go over it real quick. So from the last slide, we have this equation, okay? And we can use this equation that we have right here to solve the problem that we were doing. So if you're confused about how we're gonna do this, just look at the equation real quick. And get it in your brains. Okay. So what we're gonna do, we're gonna write out the average atomic mass and silver 107. And that's going to be equal to, we have on this last slide, average atomic mass equals mass 1 times abundance 1 plus mass 2 times abundance 2. And we don't know either of the abundances. Okay. So what we can do is, without doing like super high level crazy, maybe it's not super high level calculus, but we don't want to do calculus. Okay? We want to do algebra. So we can just choose one of the natural abundances and set it to x. Okay, and the other one, we can set it to 1 minus x, right? Because we know both of those x's together are going to equal to 1, right? Does that make sense? Why? Okay, so this one's going to be, really 107 for this one, so 107. 106. Point. 905. X of this plus 9 108.9 0.76 minus 108.904766, and after that it's just algebra. Okay, does that make sense? We can combine these x's together. So 106 minus 108, that should give us like -2 something. What does that give us when we combine the x's?
1.99. Yeah, negative 1.999.
Negative 1.99.
Yeah, 3 nouns.
999. Good enough. We're not worried about sig figs too much. It's multiple choice, right? It's not very responsible. And then we can take this 108, move it over. What do we get when we do that? Negative 1.0365. 365. And we just divide by this. And that equals x. That makes sense how we did that? Okay, and that's going to be the natural abundance of AG 107. For the natural abundance of AG 109, you just do 1 minus this under, and you get your other natural abundance. Okay. Sweet. Any questions? Oh, great. I put the word in the A.
The negative 1.0365 from.
So I took this 108. I combined these x's for the same term. I just took this 108 and I wanted to move it over to the other side, so I just subtracted. Next, we talked about light.
So it should be easier.
So you should be able to relate wavelength, frequency, and energy of light, both quantitatively and qualitatively. Basically, that just means with words and with Mach waves. Right? So just know these are some light waves, right? This is light. Light is wave and a particle, and we talked about that. Here we have. Okay, we have a light wave. This is the wavelength, right? The length of one wave. And this, the distance traveled in 1 second, is the frequency. Right? Okay. So you should be able to, you should know those things. You should also know these equations. Energy of the light is equal to Planck constant times frequency, which is also equal to Planck constant times the speed of light over lambda. Okay, and I think all of the equations are on your sheet. Pretty. Okay. Yeah. Okay. Any questions? Great. This is just something you should know. I mean, I'm going to be saying this a lot of times. You should probably just know this. You should know the order of the spectrum. So I use, remember, man, I visited your ex-girlfriend, which is not messed up.
Oh.
But it's just like, I don't know what there is. Probably not a good one. Okay. Yeah, you should just know that. Know the radio waves are way lower in energy, way longer than gamma rays. They're way higher in energy, way shorter in energy. Okay. Any questions? Next we talk about Bohr equation and the Bohr model. So you should know the Bohr model. It was this orbit thing, where this is the nucleus, and then the atom has orbits around the where the electron goes. And we use this equation to find out the energy when electrons jump either up from the ground state, n equals 1, to n equals 4, or when it goes down to n equals 4, then Sorry, guys. All right.
Special. That's the one that you get.
There's enough questions on that. Yeah,
Is the C the speed of light?
C is the speed of light, yeah. I think that is also under here. We don't have to remember that, yeah.
RH constant, is that also on our?
I think it's also on your equation.
It is. You know which the R is, oh, it's right there. I found it. Never mind.
There, yeah, I think there's a lot of them, but I think it's also one. I like to say something important though, sometimes you have questions saying, how much energy does the space?
This one is white.
You should know that that's when math wants to look, infinity as the state. Okay? Does that make sense? Okay. Okay, question about the Bohr model? Yeah.
This is only for hydrogen, right?
Yeah, this only works for one proton atoms. So like hydrogen. and some other ones. Yeah,
Like a bigger jump from 1 to 2 than it is from like 3 to 4.
yes. Yeah. But if you do the math, that should show itself too. Yeah. Yeah. Yes.
Never mind, I got it, I can see it.
Good. Yeah. Well, that's all the questions. Do a practice problem. Yeah. So do a practice problem.
This one?
So sucked up by stoic. Same question.
We didn't know. I just.
That's 116.
Bitburg.
Same one.
Oh, yeah.
That one got-
Sat down, I was like, I'm gonna figure out science.
Yeah.
But like. It's just silly. I was asking if you could go back a slide so I could write down that before you grade. Back order, I guess.
Oh, yeah, that's good. Someone just had a really good point. This equation is not on your equation sheet. You have one like it. You don't have this one, and you're gonna need this one. I don't know why they don't give you this one. Okay, but you should. You should know this equation. Just write it down, memorize it. That sucks. Memorize it. Okay. Write it down if you haven't already. Yeah.
How many times frequency?
Okay, there's the question again. How are we all feeling on the question? You solid? Yeah, you guys want 30 more seconds? We do like 20 seconds. All right. 9, 8.
Talked to a lot in the last 25 minutes.
Really?
Really?
Okay, what did you guys get for this question? Yes, if someone yell it at.
-4.08 times 10 to the -19.
Well, that's the energy or for the wavelength or for the.
The energy.
The energy, yeah. What about the wavelength? Didn't get to that? Okay, keep working on it. Keep working on it. You have to calculate the energy, and this one energy, and you calculate the wavelength. And what's the first question?
Must be like a specific unit.
It can also be nanometers.
Oh, negative.
Standard unit is.
The nanometers is like. Right? Yeah.
So you haven't used that then to get the. frequency and.
That's the energy, right?
Um,
Oh,
yes, that is.
it's this one. It's the one that's, 7. Forgot. Is RHC. 0.626. This are these 3 things. This is K. Then C. C. So, because frequency.
Where?
So here you have the same as E. And the change in E is the same as E.
Okay, how you guys feeling about this one?
Not good.
Here's the work. If you're confused about how to do it. Did you guys get close to these answers? Okay, solid. If you weren't able to do it, practice the equations. It's super important that you can take the equations on the equation sheet, know which ones to apply. Yeah,
How do we know if it's absorbed or emitted? It's based on if it's negative or positive.
sorry.
How do we know if it's absorbed or emitted? The energy? Ask the energy absorbed or emitted.
If it's negative, it's emitted.
Oh, yeah, how do we know if it's absorbed or emitted? Okay, that's a great question. When the electrons move from a higher state to a lower state, they're going to emit energy, right? Because it's like they're jumping down from something high. So I don't know, just emit energy, but it takes them energy to go up, right? Like they're climbing stairs, which I guess I'm not going with that. They're kind of like teleporting. It takes energy for them to go up. So if they go up from 2 to 4, energy is absorbed. If they go down from 4 to 2, energy is emitted. Okay? Solid. Great question. Any other questions? Okey-dokey. The next thing we talked about was the photoelectric effect. Just as a little review, the photoelectric effect is what happens when you find light with enough energy. Okay, the light that's shown at the metal has to have enough energy to become the work function. It's like the bare bones energy that's required to dislodge electrons from the metal.
Straight up feels.
Well, once it does that, any extra energy will just be turned into kinetic energy. Okay. We making sense here on the photoelectric effect? Solid. So something that was on the test, that I think a lot of you guys missed was how, let me ask you guys a question. If I was to shine, actually, let's just go to the next slide and I'll ask you guys the same question. Okay, this is a little practice. So let's look at part A, or actually, okay, so just read it. Look at part A. Let's ruminate. And then just let me know what you guys think. What do you guys think for part A?
Yes.
Yes. Why do we know that?
Blue light has more energy than red.
Blue light has more energy than red light. Yeah. Okay. Sounds like you guys are all pretty solid on that. What about B? Read B, think about B. Try that as well. What do you guys think about B?
Not necessarily.
Okay, is the answer no or yes?
Yes.
The answer is actually yes. Okay. Because the only thing that dictates the amount of electrons is the intensity of the light. As soon as the light, doesn't matter if it's blue or red, if they both have enough energy to work on the work function, then they're both going to dislodge the same amount of electrons if they're the same intensity. So if we want to dislodge more electrons, we increase the intensity of the light.
Is incident just like, kind of like another word for like exposure, like area covered in this case?
I think that just means it hits at the same angle, you know, they have like similar striking, you know what I mean? Yeah.
So how does the intensity change? Is it like the amplitude or?
Yes, the intensity of the light, it's just more light, it's just more photons. You know what I mean? If you have like 10 photons compared to 1,000,000 photons, one, you're not gonna be able to see at all. And I don't know if you'll be able to see 1,000,000 photons, it's gonna be a lot stronger, a lot more visible light, it's a lot more. Okay, so the way you get more electrons dislodged is by increasing the intensity. So what about part C, what do you guys think? Yell it out.
Speed.
Speed, right, kinetic energy of the electrons that are dislodged. Okay, so these three things, mostly part B and part C, were kind of things that a lot of people miss. I think it's a good thing to review. Any questions before we move on? Okay. The next thing we talked about was the Broglie wavelengths. We talked about this because we talked about orbital next. Basically, when matter's in motion, it has a wavelength. Doesn't matter what it is, it has a wavelength. This is the equation for it. So we have a little question we did last time. So work on the question. Something I thought was a little funny was my brother looked up the speed of a bullet, and it's about 100 meters per second. Wait, I didn't think about that for right, but anyways, here's a question. Come up with an answer. And okay.
He has the fire. That's right.
Very question.
Strong. Is it to play with or to eat? That's a lot. Here, you want to take some? Let's see. So what? Like 6 weeks? Yeah, it's a lot. I got so much.
Okay, guys. Good for your answer. Did you get this? Okay. Everyone good on the Broglie wavelengths? We're good on unit? Units are super important. Yeah, let's move on. That was all the stuff we have to go for unit 1. Anyone have any questions on unit 1 before we move on to unit 2?
So when we're talking about wavelength, it's frequency, I forgot which way. Is energy increased like mass?
Energy is directed to like
I just had a question about, is it gonna be equally, it's gonna be like equally dispersed, or is it gonna be slightly different? Stuff out, yeah, but that's fine.
Like, pretty good. It's supposed to exams like Chem, just whatever
has the most
tomato. I usually like B. Yeah, I need
coming up. On right now.
I'm really gross.
Okay, guys, unit 2. Unit 2 was super fun and everyone loved it. So we talked about orbitals. So does everyone remember brain?
Every single bit.
Okay, do you remember the quantum numbers?
The worst.
Wow, not good.
I like eating.
Questions about this? You know what I mean? Because it's kind of like,
We did have to re-memorize it.
you guys want me to just go over it again?
All of it.
Yeah. Okay.
It's like, I don't even know what you got to ask. Just say, what is
Okay.
Very, not, you know, like, two.
So, first thing we have is principal quantum number X. Okay, I know these are letters, the column numbers, we're confused. The first number is n. This is our shell. If we go back to the Bohr model, we have n equals 1, n equals 2, n equals 3. This is kind of what we're talking about. It's kind of like how big the orbital is. Okay. The allowed value for this one are just n, right? This one you always be given n number, and this is also directly correlated to the periodic table, right? This is n number 1, n equals 1. This first period, the second period or second row, n equals 2, n equals 3, n equals 4, n equals 5. You know what I'm saying? Yeah. Solid. We solve it on quantum number n. So, next number we talked about is angular momentum, or L. This is the subject, right? This is if it's an s orbital, or a p orbital, or a d orbital, or an f orbital. I don't think we talked about f orbitals too much. But it's a subject, okay? So the allowed values for angular momentum of L can be anywhere from 0 to n equals 1. Okay, so if we have, let's say n equals 4, we can have L that equals anywhere from, we can have an L from 0, we can have an L of 1, we can have an L of 2, or we can have an L of 3. Okay, what subshell is it if L equals 0? S. Okay, what about if L equals 1? 2? What about 3? Okay, you should know that. Very good. Any questions about L? You should know what an s orbital looks like, what a p orbital looks like, and you should know what a d orbital looks like. Okay, which sounds, like everyone knows it. Well, a lot of people kind of miss this drawing question on the test. So you should be able to look at the orbital and know what an L is about. Okay. The next one we have is the magnetic number. This is the m sub L. Okay. So this is the. This is the which orbital is this? This is kind of like the orientation. This one. Because you can have a p orbital that goes like this way. We could have it go like this way or this way. I don't know. You know what I mean? Yeah, you know what I mean. Everyone else know what I mean? So this is what we're talking about with m sub L. We can have a px, which goes along the x-axis, a py, where it goes along with the y, or a pz, where it goes along with the z. This is m sub L. Okay. M sub L, the rule for that is it can be anywhere from negative L to so if we have n equals 4, our m sub L can be anywhere from -3 to 3, with everything in between. Okay. Okay. The last one is the spin. Okay. This one is either 1/2 or -1/2. It's just saying that in each orbital there can be 2 electrons, and they have to spin different ways. They can't be spinning both the same way. Okay. You don't remember when we did the electron configuration? We draw one arrow left and one arrow down. Okay, that's to indicate the spin. Okay, so are we doing okay with that review of quantum numbers in orbital? Anyone have any questions? Yes.
Oh, could we talk about like nodes really quick?
Nodes, yeah. Great question. So if we draw an orbital, just an atom orbital, let's say n equals 1. Let's say this is hydrogen. Great. So our L is completely 0. And we're not really concerned about n about because it's 1s. It's only 1s. Okay. So this is our 1s. This is our middle proton. No nodes. But if we have something like a p orbital, there's this spot in the middle with no electron density. My drawing is just bad. It looks like there's some electrons there. There's no electrons there at all. Okay. And if anyone's struggling with what orbitals are, it's just a cloud of electron density. It's just anywhere the electron could be at any one point. The electrons are moving too fast. So it's kind of like it's the whole thing is full of electrons, but it's just like 2. Okay. So that is where that's a node. But if you have a d orbital, two nodes, okay? And those are both called what? Angular nodes, planar nodes. Those are both planar nodes, okay, on both of those things. So the way you find the total number of nodes, if you're given quantum numbers like n and l, is you do the total number of nodes is equal to n minus 1. So if we have n equals 4, how many total nodes are we going to have in our orbital? 3 nodes. Okay. What if we have L equals 1? How many planar nodes are we going to have?
P1.
1. That's great. Why do you say 1?
It's the same number as L.
Right. The planar nodes is the same number as L. Whatever your L is, that's how many planar nodes you're going to have. And again, these are planar nodes, right? Where it goes in the plane, with no electron density along that plane. Radial nodes are different. It's the total nodes minus L. Okay, and radial nodes, if we had n equals 4, but L equals 0, what orbital would that be, first of all? S orbital. But we have 4, right? So there's going to be 3 radial nodes. Let's just pretend these are our radial nodes, right? The little lines, those are radial nodes. We can have like orbitals this way. All right, that's a bad picture, but you guys, right? Okay. We're doing okay on nodes. Conceptually understanding. Okay. Does anyone have any questions? No. Okay. If you're still confused, watch a YouTube video. I think Dr. Stetson had some really good Khan Academy ones. Just kind of stare at this chart for a while. Good work. I think you did some homework on this, so revisit that. Okay, let's move on. Oh, this is just another slide about nodes and orbitals. Kind of like a different chart. If you get bored of this other one, look at this one. Okay, so let's talk about electron configurations. Okay, does everyone remember electron configurations?
Yes.
Okay. So, just remember that you can use the nuclear gas as kind of a shortcut. If you have aluminum, you don't have to write out this long thing, right? You don't have to write out this long thing. We already know what neon's electron configuration is. We just write neon and then the next of aluminum. Okay, that makes sense? I want to spend a little time to talk about copper and chromium, which are exceptions. Basically, the exception is when we're coming up to d orbital. I also want to talk about what happens when we lose electrons, when we have electrons in d orbital. Yeah.
Yeah.
So can anyone tell me what the electron configuration of copper is?
Well,
Let's just start out with the noble gas. What's the noble gas component? Argon. Okay. And then what am I going to write?
3d10.
Okay, let's go along the road. How about that? So we have 4s. Where's my things?
4s2.
We have 4s1, 4s2, and then we have 4s2 3d1, 4s2 3d2, 4s2 3d3, and then when we get here, what happens? We have 4s1 3d5. One of the s's went to the d orbital because the d orbital is higher in energy and it wants to be stable. It wants to be either half full or completely full. So we're fine if the s isn't full, but the d orbital can be half full. So when we get here, it was like at vanadium or whatever this one is, it was like 4s2 3d3. Then it was 4s1 3d5. At this next one, what is it?
4s2
4s2 3d5. And we just keep going. 4s2 3d6, 4s2 3d7, 4s2 3d8, and then at copper it's 4s1 3d10. Okay, what is the electron configuration of copper plus? Okay, so if we lose an electron, we have 4s1 3d10. Where is that electron going to be lost?
S.
Or the s. So the electron configuration of Cu plus is going to be argon 3d10. Okay, so we lost the 4s because we'd rather have a full D. There are a lot of people. This was like the most missed question on like midterm 2. Yeah, does this make sense what we did there?
Would that be considered like its excited state or just its ground state since it's exception?
That's a great question, and I have no idea. I don't know. Great question.
So
Yeah,
it was just CU.
Yep.
Would it still be, how would that change it?
if it was just CU, it would be argon, right? The electron configuration of argon and then 4s1, 3d10. But if this loses an electron, we don't want it to lose from the d orbital. We really like the d orbital to be either half full or full.
Because it's not.
Okay, we need that.
It's the exact same.
Okay, great. Any questions about electron configuration? Yes.
The ion that's made transition metals, right? You take from the s orbital instead of the d orbitals to make the ions.
If in the non-charged state, the d is either half full or completely full, then yes.
Okay, but not if
But if
it's,
you had something like 4s2, 3d3, it would go 4s2, 3d2.
Just those two calls.
okay,
Yeah, you just lose from the d, because it's not either half full.
okay.
It's too cold.
Only when the d is half full or full. Weird. Okay. So it's weird. You just gotta know that. Any questions before we move on? Yeah,
There's the cation for, you also do the same thing as copper.
yeah, so the cation for chromium goes like 3d5, right?
In the case of like a half full p orbital, does it sort of follow a similar trend or not really?
No. No, we're never gonna worry about it. It's usually just d orbital. Great question. So, you were asked about this ground state versus excited state. The ground state is just the normal state, right? It's what we have here. The electrons, it's 4s2 or 2s2, 2p2. Then we add energy, so it gets excited. So it goes 1s2, 2s1, 2p3. Right? There's no ground state, excited state, like what it's talking about when we're talking about ground state versus excited state. Confusion there? Yeah, let's move on. Why did we have this? Oh yeah, you should be able to know what the alkali metals are, the alkaline earth metals, halogens. You can know what the noble gases are. You can know metals, you can know alloys, you know the non-metals. We still on all that. Okay. Yeah.
What are the 7, 8, and 9?
Ready now?
Yeah.
These are non-metals.
You have to know the specific names.
Nitrogen, oxygen.
No, like the groups.
Oh, yeah. I don't think you have those. But I don't think you have any. Sorry, I don't understand your question.
Yes.
Here are some periodic trends. So honestly, I would just memorize this chart, right? And we talked about it using like the orbitals, the G effective, and the N level, right? The shell. Still know how to do that, but basically just know if you know list which atom is more negative than the other, which one has bigger atomic radius, which one has higher ionization energy, that's.
I think we'll have to be able to explain like why is that way.
I don't think so. I really don't think so. If you are gonna have to do that, I think you can just do the chart. Just see effective. Yeah. Yes.
Can you talk about some exceptions here? I know there's some interesting stuff going on with like oxygen-ish region over there.
Okay, yeah, so this region up here is fluorine, oxygen, nitrogen, super electronegative. And the arrows up here say electronegativity goes up this way. But this actually isn't true. This last column of noble gases, they're not electronegative at all, right? Because what is electronegative? Anyone define it for me?
How much it wants electrons.
Right, it's just how much it wants. Okay, and the noble gases, they have full valence strength. They don't have electrons at all. So they're not electronegative. I think it's the same thing with electron affinity. Something like that. Did that answer your question? Yeah. Was there anything else you're wondering about?
Yeah, I just remember there's like, there are two things like right on top of each other, like upper and silicon, like chlorine that have like some weird trend. For one of the tests. I know it came up on the test, but I don't remember.
He's talking about how nitrogen has a. Something like that, has a different like value than expected.
Oh, exactly what you're talking about. Okay, so I think what you're talking about is the atomic radius. It just has to do with the fact that oxygen, where's oxygen? Nitrogen has a half full p orbital. So it's going to be a little. I know exactly what you're talking about. I don't think you're gonna have to look up fast. But that's a great question. Yeah. As long as you know these trends, you can do fine. Yes, question.
My question was similar. I think it was gallium is smaller than aluminum on the periodic table.
Yeah,
And so I just know like what.
I don't think you're gonna have to know those obscure. As long as you know this, you'll do fine. Yeah.
What about reactivity?
What about it? Depends. Well, usually if it's more electronegative, more reactive.
Francium, like one of the most reactive elements.
Where's francium?
There's just the electron flux.
Oh, right. It was the electron cloud was so big.
I think I saw reactivity. That is one of the.
Yes.
And just really quickly, why is atomic radius? Why does that arrow have it getting like smaller or on the left? So like atomic radius, doesn't it like increase from left to right?
Decrease from left to right.
In practice.
No, atomic radius is super small over here, like pretty smaller. Well, hydrogen is small, but out of all the other ones, hydrogen is there. Fluorine is small. And it kind of decreases going from here to there.
So why is it doing that again?
Why is it doing that? Because it has to do with Z effective and also the N. The Z effective, if you remember it, is just the amounts of pull from the protons on the electrons.
Okay.
And there's not a lot of, there's not at all any shielding. Well, I think maybe there's a little shielding on fluorine. It's just the protons, the electrons are so close because the N is so small.
Yeah.
The protons can pull on the bottom. So that's to do with the N levels really small, so the orbitals not very big. So the effective is really large. Okay. Solid. Any more questions? Periodic trends? Okay. Move on. It's fun stuff. Actives. Yeah. Okay. Ready, set, go.
You know if we're gonna have an electronegativity chart for this?
I don't know if you're gonna have like I would say probably not. But maybe.
Probably not, but maybe.
Much more
on that.
Maybe. I don't know. You might have it. I honestly don't know the answer to that question.
To least electronegative oxygen is the most. Would it be and
It's like a one of four.
Yeah. What do you guys think about the first one? What is the ranking?
Oxygen's highest.
From most to least, someone tell me.
Oxygen.
Oxygen.
Phosphorus.
Phosphorus.
Hydrogen.
Chromium.
Maybe high.
Chromium. Oh, sure.
Yes.
Yes. Okay, we're sure with chromium. What's next? Hydrogen and then rubidium. That's very good. Someone want to pull up an electronegativity? Just verify these two. So this one's around 2. I don't know if chromium is around 2. I think hydrogen. More electronegative. than chromium.
Hydrogen is more electronegative.
Yeah.
Hydrogen has a similar electronegativity to carbon.
Yeah, so hydrogen and carbon are pretty much the same. Why would we have something like,
It says hydrogen and phosphorus are the same.
there's more?
Yeah.
Yeah. Can you guys see? Okay. This is the most, the least.
This chart says that hydrogen is higher than phosphorus.
Hydrogen higher than phosphorus?
Yeah.
Honestly, now that I think about it, you probably will have. Either you will have an electronegativity chart, or you won't, and you won't have to deal with any problems like this. Okay, so either way, you'll be able to do it. Okay. So if you have something like this, just use your chart, compare values. You should know the trends. That was my fault for thinking ones are kind of.
We'll say that phosphorus.
This next one should be easier, right? What do you guys think the answer is for the next one?
So it goes sodium.
Just as small as someone's done with that.
And those basically what's the
Sodium?
Sodium, carbon, chlorine, it'll be big down at three and
Sounds right to me.
and then sodium.
And then sodium.
So,
Carbon.
so,
Honestly, I don't think you'd be given a question like that where you have to compare the N level versus the low Z effective, high N level versus low Z effective. And you won't be given a question like this. This is just me being really bad at writing questions. Okay. So that one was confusing, but you understand the concept, right? As long as you get the concept, you'll be fine. Yeah.
As far as like the sodium, like tin is like 2 rows down the table, so it's like way larger.
I think, I do think tin is larger than sodium.
Significant.
Yeah.
That's what I'm saying.
Yeah, I definitely think it is. But I think the questions you might be doing are gonna be. Anyways, we're gonna talk about bonding now, okay? So, you don't wanna be here forever. What? I know, what's crazy? So you should know bonding. You should know the difference between ionic bonding, covalent bonding, and metallic bonding. You should know what difference in electronegativity gives each. Pretty much that. Okay. Any questions about bonding? I feel like we all know what a covalent bond is. Yes.
Are we gonna have to know like the number value for if it's ionic or covalent?
Yes.
Okay.
Now, you should know 1.8 is when it starts being ionic. You should know 0.4 is when it starts being polar covalent. And anything less than 0.4 is gonna be just non-polar covalent. Yeah.
so all of the post-transition metals you don't actually use any metallic bonds?
These ones? The transition metal?
You're saying post
Everything else?
Yeah, like aluminum and stuff.
metals that are.
But they're not actually.
Yeah, I don't think that is equal. See this pair, okay? So you should know the metals versus the metalloids.
Okay, I'm just wondering, like the chart, it cuts
Yeah.
out the utility bonds.
It's just that it's not great. This was, I found this on the other. Yeah. I don't like the language. Sorry about that. Yeah. All the metals, all the metals.
And just so we're clear, it's always going to be ionic between a metal and a metal, even if
Yes, because the electronegativity is so big.
the difference between them isn't.
Well, if it's not greater than. I don't think so. If it's not greater than 1.8, like, sure.
I remember I had a question.
I don't think it would be.
Like, for example, there's like.
That sounds like very deadly. You read it once, license your lungs.
I think manganese is not part of it. Manganese would be. And there are compounds like MnO4 that are very, we're gonna use them a lot. Especially lactose. Sorry. That's the reason why I'm sure about it. Does that make sense? So if the difference in electronegativity is less than 1.8, doesn't matter what it is.
I think I had a question out. Like, Bill said it was.
Yes.
With, metalloids, those do metallic bonding.
I think they can do either. Honestly, I'm not super sure, but I think you don't have to. I think you just look at the difference in electronegativity and that'll pretty much tell you. So yes, I mean, great question. Okay, let's move on. Next thing we talked about was hybridization. We talked about how those orbitals we talked about, the S's and the P's, they can combine when they're bonding with things to give better bonding orbitals. Right, this is valence bond theory. So if you, so an S and a P orbital, if there's two things around it, it's sp hybrids, right? So say we have like what is the hybridization of that C in the middle, the carbon? SP, what is the hybridization of that C? SP2, right? You guys understand what we're doing here with hybridization? You guys understand the concept of hybridization? Does anyone have any questions? Or are we feeling kind of good on this one? Yeah.
So, are we like counting lone pairs as a thing like this?
Yes. So lone pairs, so if we had something like NH3, which is ammonia, if we had N, E, A, H, and a lone pair, what is the hybridization of that nitrogen? SP3. Okay, the lone pairs do count as a region of electron density. So that's all we're counting is regions of electron. Okay, yes.
But double bonds only count as one region.
Double bonds only count as one region. Okay, that is another great question. Single bonds also only count as one. For hybridization. Another thing you should be able to do is you should be able to look at the hybridization and know the geometry. Okay, so we look at CO2 and we're like, wow, that is SP. That looks really linear. It is linear. We should also be able to look at something like C. Methane, right? There's a lot of stuff on this board, but the CH4. We should be able to look at the CH4 and say, wow, that is tetrahedral because it's sp3 hybridized. So is the NH3. That is tetrahedral. Okay. So refresh yourselves on the geometry. It's going to be tested. Okay. Any questions about hybridization? Yeah, this is just another chart. You should probably know the bondings. You should know all the names. Just know the chart. Okay. Okay, let's go on. Next thing we talked about was sigma and pi bonding and anti-bonding.
Yeah.
So we talked about how when atoms come together, their orbitals kind of combine. They go from atomic orbitals, which is like the sp and the sp3, to molecular orbitals. Okay. Which is like this, what we have right here, right? Let's look at this one on the bottom. This is sigma bonding right here. This is sigma anti-bonding. So every time you have a bond, this is a single bond between, let's say, two carbon atoms. Okay, this is the sigma bond. But with every single bonding orbital, there's an anti-bonding orbital, even if it's not. Okay, so really interesting.
So the bonding is where there's the big thing in the middle, the anti-bonding is where they.
Yeah,
The top is anti-bonding. Of the signal, the top is anti-bonding, the bottom is bonding.
right. And these colors, really aren't, they're not right. I don't know who made this, but not a great job. On this one here, it should be shown that this is out of phase, so you should have a little blue from here, and this one should be white. So that they're kind of out of phase, and so they're not combining constructively. Basically, what it means is that when we have this guy, we also have this guy. But it's just not full of electrons most of the time. It can be with the electron configuration chart that we're doing, and we're going to do a practice problem with that, right? Yes. So bonding is where the atoms share the electron density. The electrons go everywhere in between, none on the two nodes. The anti-bonding, if we fill up the anti-bonding with electrons, the bond between the atoms will break. Okay. So, and this is for the pi bonding and anti-bonding. This is anti-bonding. The bonding. You okay on that? Any questions? We're gonna do a question, practice question on molecular orbital diagrams. You should remember what paramagnetic means and what diamagnetic means. Paramagnetic means that it has unpaired electrons and it's going to react to an electro field, right? It's gonna be kind of magnetic. Diamagnetic is where all the electrons are paired. There's no unpaired electrons, and it's not gonna be super magnetic. Yeah. We don't have to worry about drawing the MO diagram. I don't even do. But you should be able to fill it up with like Apfau's principle. Just basically just use common sense, right? So if you have, we're gonna do a practice problem right now. But you fill them singly, they all have different spin, you go from low to high. Okay, yes.
Would we be asked like about like those specific things, like, oh, what's Clem's rule or what's like this, or do we just need to know how to apply it?
I think you should just know how to apply it.
Okay.
Know what they are, but I don't think you have.
Okay.
Know what they are. Okay, so let's do the practice problem. Ready, set, go.
Where were you just playing? That's what it is.
I'll play the answer. Oh.
Back to my dear. You got the shirt? That's all that matters.
We got it wrong.
Eight minus two.
For F2. What should I?
This.
I didn't actually want to. Sorry. F.
So having 7.
Two, there's two Fs, one plus. That's my bad. I'm sorry about that. It's two Fs, one plus. Great question, sorry.
That would make 13 electrons. Has 3 in pi. It's non-star bonds. And I am bond order of. Yeah, so bond order actually just with the original. Luma was the. I had forgotten this flag, but. Oh, never mind. I got some stuff.
Seven.
You lost. We had one more. No, the bond order is diamagnetic.
Do you know if it works? I don't wanna like announce it. It's like.
But the bond order of 2. This one is pure. Occupied F2 per the planet. Occupied. Stars. Just lowest unoccupied. No, sorry. Highest occupied.
Star one.
Unoccupied.
Yeah, the 0 2. Well, and because it gives you this is the one. This is the one that has the whole.
Okay, guys, so what should?
I would settle on it can do what less. Sooner than you do it the
Two F, one plus. What should that look?
Oh,
That's great. So this one is. It's worth learning how to.
That would also.
It would have 14 electrons.
You know something, I bet. Know something, I bet. That's a story.
Okay. So what am I gonna do? Oh.
Down, down.
That's it.
Okay, so, did we all get that? Did we understand what happened? Okay, so which orbital is the HOMO?
Pi and wanting to.
Star.
Pi star,
Yeah.
pi 2p star, right? Okay, this is the HOMO. This is the highest occupied molecular orbital. And then what's the LUMO? Which orbital is the LUMO? Right, the sigma star 2p. That is the LUMO. That is the lowest unoccupied molecular orbital. Be able to distinguish between those. Fine. So what is the bond order of F2?
1.5.
1.5. Very good. Is it paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic because it has unpaired electrons. Great. And then how does this compare to normal F2? What's the bond order of normal F2? 1. Very good. Is normal F2 paramagnetic or diamagnetic? Diamagnetic because it has one more electron, all the electrons would be paired. Diamagnetic. Very good.
These bond orders too.
This one's the very end. Whoa, there.
Gosh.
Wait,
Too far?
I go
Okay, good. Wait. The next thing we talked, yes, sorry.
Can you go on to?
Yes, okay, that's a great question. So to find the bond order, you're doing this. What you're gonna do is you're gonna do all of the bonding. So bonding minus anti-bonding over 2. That gives you your bonding. Yep.
I didn't know.
Yep.
Failures.
So,
The-
yes.
How do you get the number of arrows again?
Number of arrows, that's the arrows are just electrons. So what you do is you have F2, you don't have 2s. So F has 7 electrons. Okay, is that right?
That's 7 valence electron.
7 valence electrons, very good. So F has 7 valence electrons. Yeah, you can always pair about at the end too. So we're just looking at the electrons on the end. We have 2 with 7, so 14, and we have a plus, so minus 1, so it's 13.
The star, like star.
Bonding is the not star. The anti-bonding has this. So sigma is bonding, sigma star. Okay. That makes it pretty long. The next thing we have is naming of ionic compounds. There are going to be questions where you're going to be given a formula and you're going to have to name it. Either you're going to be given the formula or you're going to be given the name. And you're going to have to know the name. You're going to have to know the formula. Okay. So when you're naming ionic compounds, you should name the cation and then you should name the anion. It's simple. So if you have something like NaCl, what would NaCl, what would the name of that be? Sodium chloride. Sodium chloride. Very easy. You add an I to the end of the anion. And then when you're doing transition metals, it's not always clear with transition metals what the charge is going to be. So iron can be +2, +3, or +4. Okay, so if you know you have iron +3,
Inhibiting my.
you're going to write iron 3 with parentheses oxide. Okay. So, questions. The next thing we have is covalent compounds. When you're naming, this one's a little more complicated. When you're naming the covalent compounds, you're going to do most electronegative atom first. Or sorry, less electronegative atom first. Put the less electronegative atom first. So if you have something with oxygen and oxygen is usually going to be the last one. You're going to use the Greek prefixes to indicate the number of atoms of each element. So like mono, di, pro, or tri, I think. Tri, tetra, penta, sexta, hepta, octa, nona, deca. Let me know if it's tenure. Thank you, thank you. When you're naming the first element, don't use mono. So no like mono sulfur oxide or whatever. If it's the first one and there's only one, no mono. No do mono. Know that. Yeah, prefixes, these are just like, I don't have any questions with this. Remember it from unit 2. Okay. Well, if you don't remember your polyatomic ions, now is the perfect time to remember them again. It's one of those things. So memorize this. It's honestly not super hard to memorize. You've already memorized it, hopefully. If you haven't, then memorize it all. If you have, good for you, maybe easier to memorize again. You just gotta know. So there are gonna be like word problems saying you have this many grams of. Okay, and it does a reaction, blah, 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 blah. You should know what carbonate is, you know, and be able to draw. Okay. Okay, let's move on. Let's do some practice. What are the names of the first two? What are the names of these first? Sulfide. Super tough stuff. We gotta go. Okay, we're not gonna give, we don't really have time to do all of them. But if you want, you can go back and do it. These are not the answers. These are not the answers. This is different. If you're given the name. So. This is for covalent. So what are the formulas of these first two? NO. N2O. Okay, not the hardest one. You guys understand the concept, right? So you need extra practice. There's more practice problems here. Online, yeah.
So what are the rules with like eights and us? Yeah,
We're about
so I know those. We don't need to know those. I'll just like.
I looked for study guide and said if there was nothing about naming acids on the study guide. Great. But I didn't put anything about it. But if you want, and if you're feeling like paranoid, then you're gonna be on the fine name. Let's go back and look at my exam 2 review. Here's like 5.
I'll take your word for it.
Okay.
Let's study. That's Dr. Sanson.
No. Okay. This is just a little nomenclature flip chart. Which one's the rules? You can use this chart. I don't worry about it too much. Back to the chart for a second. Yep. Blue structures are like. Okay. Next thing we talked about, two structures. We should all, at this point, be good at drawing Lewis structures.
Yeah, really, I feel
Do we all feel confident? You think we need to get
How do you do with like odd number electrons?
like radicals?
I don't know, because there was like one on the test where it wasn't like 7 or something.
It was like NO2, wasn't it?
It's just.
Yeah, I think so.
NO, so if you have NO is a great, that's a great example. That's called, when you have an odd number, it's called a radical. I don't know why. So we have NO. How many bonds are gonna be between molecules? Gonna be a double bond or a triple bond? Double bonds. Okay, how many alone pair for each atom gonna have? So you want oxygen.
I thought that was a negative sign.
How many lone pairs on there?
Special.
One double, one
Very showing that is.
Okay, and we understand how we got this Lewis structure. So if we have just N and just O, and there's no chart, this is not a chart. Just N and just O, and it says draw a Lewis structure. What we're gonna do is we're gonna find the number of valence electrons. So N has 5, O has 6. We add them together, 5 plus 6, that's 11. Okay, so what we did was we first connected the N and the O. So you just do a single bond first. And if you don't know, I know, just do a single bond. Then find out how many groups each atom wants. So oxygen has 6, it wants 6 around it in order to minimize formal pressure. Nitrogen it wants 5 electron groups around it. So we gave it 5. Okay, and that adds up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it can be a little weird just throwing a single electron on nitrogen. That's called a radical, and if you have an odd number of electrons, then you have a radical.
Actually, yeah, I got
Okay, solid. Any questions? Okay. Another thing we talked about was resonance.
Resonance.
So you should know the definition of resonance. You should know that.
This is giving
in
me a lot of
resonance,
grief.
Electrons are delocalized.
I do it.
Right? It's not this one, it's not that one, it's the one on the bottom. It's like a hybrid. Okay, it's never just this, and it's never just something like this. Right, where each molecule has a partially charge. Okay, does that make sense? You solid with, resonance? There are some guidelines for resonance. So first of all, draw your Lewis structure is good. Second of all, when you're doing resonance, don't move the atoms atom. If you're moving your atoms and you're doing resonance structures, you're doing it wrong. So don't move your atoms. It's just when electrons move. Okay. When you draw resonance structures, each resonance structure should have the same net charge. So all the formal charges should add up to the same thing. Okay. You should maximize bonding. You should minimize formal charge. And when you're trying to figure out which one is most favored, contributes the most, a lot of times we'll say that. It's going to be the one where the electronegative atoms have the more formal charges. It's going to be the one where there's less formal charge, and it's going to be the one where bonding is maximized. Okay, these guidelines kind of make sense. I know it was a lot of earlier, but it makes sense. Okay. Okay, let's just do like 2 of these. I don't do all of it. So do HCO3 minus and ClF3. Draw those 2 Lewis structures. We can do that yourself. One of them are kind of easy. Okay, we're only halfway done.
Hungry again?
I'll run a second one.
You hungry again? I'm good. Do you like it?
Okay, everyone good with what these Lewis structures look like?
Okay.
Were you guys able to draw resonance if there was resonance? So if you see that the structures you drew are able to have resonance structures, draw the resonance structures.
Like, why was copy on copy?
Okay. So, feeling confident? Okay. Move on. Any questions before we move on? Okay. Another thing we talked about was bond length and bond strength. It's pretty simple. I mean, the higher the bond order, the shorter the bonds. The reverse is also true. So the lower the bond order, the longer the bonds. When you have bigger atoms that are bonded to each other, like let's say bromine, we have Br2. That's going to be a really long bond compared to F2. Yeah, it's smaller. So it's going to be a shorter one. And for bond strength, more bonds, the stronger. I mean, if you have a double bond, stronger than a single bond. Triple bond, stronger than double bond. Okay, any questions? This is just the chart again. I don't know why I have it twice. I don't know. Well. Okay, one of the last things we're going to talk about is the polarity to this unit that we did talk about. So a molecule is only polar if it contains polar bonds and it's not symmetric. So if a molecule has polar bonds, but it's symmetric with its polarity and all the dipoles cancel out, and it's not polar. Okay, so pretty simple. Let's do some practice. I want you to look at these four molecules. And tell me if they're polar or non-polar. Okay, talk with your friends, your associates. You think they are?
How many? Electrons. Yeah, you don't have any lone pairs. PCO's pretty accepted. PCO's right, because more like, yeah, in order to give it a double bond, it makes CO. Electronegativity makes it makes so CO2. That one's gonna be it's S and CL have like different 5 plus. Is it really? I can't read I've got it'd be molecular. Yeah, because that could be the bonds, but it's the shape. It is, that is. It'd be trigonal pyramidal.
Okay, CL3.
Non-polar.
Non-polar, are you sure? Final answer, yeah. You're non-polar. Think about Sokol. Polar. Wow, you guys are so smart. What about NBR3? Non-polar or polar?
Polar.
It is non-polar.
Oh,
Super close.
oh yeah, that'd be good, yeah.
Oh, yeah.
What?
This is the electron.
I just like the cascades of, oh yeah, now I get it.
We understand why it's non-polar.
Could you explain this one?
So when a BR is bonded to an N, is it a polar bond? Yes.
I don't know.
It's not a polar bond. The electronegativity difference is not greater than 0.1. So even though it's not symmetric and there is a lone pair on the nitrogen, it's non-polar. The bonds aren't polar. Does that make sense? Yeah.
You explain why BCl3 was non-polar?
Why BCl3?
Yeah.
Because boron only makes a green bond. And it's happy like that, with 6 valence electrons. So, you're gonna say, when it's happy like that, this is trigonal. Trigonal plane. Symmetric. Even though that these are super polar bonds, they don't cancel each other out.
Why is the shape symmetric? Because can you cut it and not be the same on either side?
Because it's a triangle. Yeah, yes. But we're not cutting it.
Oh, maybe I'm not thinking about it.
Oh, what do you mean?
What do you mean
I
by,
don't understand.
what do they mean by symmetry again? I don't know, I was,
That's a great question. So that one is a triangle right there. So
That's rotational symmetry.
reveals symmetry.
means I guess not symmetric, but it just means that all the polar bonds kind of cancel each other. They're all kind of balanced. Right, because you have a polar bond going this way, but you have one going this way. And like net 0.
Okay.
Okay, awesome. Now what about SF6? Non-polar, very good.
T-shirt.
I want to kind of trip you guys up a little with NBR3. Okay, the final things we talked about with unit 2. We're almost to our break. We're almost to the spot where we can have it. One of the final things we talked about with organic chemistry, we talked about functional groups. Okay, and it looks like a lot, it's just 2 charts of the same thing, there's just subtle differences, like this one, it's 2 charts, okay? A lot of them are the same. The ones you should know, I put a list in the PowerPoint of the ones you should know. You should know alkenes, double bonds, alkyne, aromatics, alcohols, ethers, aldehydes, ketones, esters, carboxylic acids, amines, and it's just 11. If you know 11 structures, you're okay. And honestly, most of them are, I mean, yeah. You don't have all. But as long as you know these 3 charts, you get, you don't have to know everything, like you don't have to know a diamine, you have to know that. You don't have to know hydroxylate alcohol. I don't know what it is. But, okay, you good? So it seems like a lot, it's really not. I mean, if you take 5 minutes, like trying to draw them out, like trying to memorize them. Question.
Alright.
Okay. Let's talk about isomer. This is the last thing we talked about in unit 2. So isomers are molecules with the same chemical formula, but different structures. So you can have different types of isomers. You can have structural isomers, where they have the same formula, but they're built different. Right? Like we have C3H6, and it's like that, like a triangle. Or we could have like that, right? Oh, I guess that's not C3H6. That is. Right, those are structural isomers. Okay. Same chemical formula, built different. You can have stereoisomers. Same connectivity, different arrangement in space. Or we have the geometric system trans. Let's just take this. Is this cis or trans? It's trans, because they're on different sides. What about, well, I mean, it's kind of now, but it's cis. Right, you understand? So geometric isomers, cis and trans, is usually only with double bonds. Yeah. Okay. The last one is optical isomers, chiral centers. Usually it's carbons. You guys remember optical centers, chirality? Yeah. If you don't remember it, we don't really have time to go super far into it. I would just go back and look at your notes, maybe look it up online. You should know that. And then here's a little flow chart. It kind of has all the different isomers. You get, I mean, pretty. Yeah.
We have to know about the enantiomers and diastereomers.
I don't think you have to know about the enantiomers and diastereomers. If you know that part of the chart, it's my bad for not. Here's another chart. Okay. Honestly, only worry about for the optical isomers, just worry about the enantiomers, don't worry about the diastereomers. So the enantiomers is just, that's what we're going to call it. Okay. Should be good. Are we all feeling okay? If you're not feeling okay, again, go back in your notes. You can email your TA, you can email me. You can have a little more time. I just don't want to like keep us all here for like a million hours. Speaking of that, let's take like a 5-minute break. If you want to leave, now's the time. Record it, so I don't feel too bad. Don't stay.
Pretty well. You just
All right,
really.
5 minutes, then we're coming back.
You're going up down aggressively. Wait, no, you're right. That mouse. Yeah. That's so surprising.
My understanding is that all really have enjoyed the tests and the
Slides are.
That'd be the same, but especially traffic. I think this class. Yeah, I don't think. It'll be young. Even cat can definitely need to go over. Kind of longer. I need to go with that stuff probably. Even though my text. She's she forgot like 40 on the test. Fish kebab. Like, oh yeah. Most I got was nice studies are. To be a good student. Yeah.
Yeah, I can still be a good student. I still have to remember all the best.
I don't know.
I'm ready. Okay, email that.
That's exactly. I'm also like my starting. That is too hard.
Or is it about 3 kids?
So we're gonna speed run through this next one. We don't need that. We're not about it.
Friday.
Probably better than the midterm.
Saturday. And then.
Better than the midterm. I think, yeah, it responds. A lot of the time. Well,
Everything else like.
but people.
I am.
I think a lot of people will do worse. I think more people will do better than. It's also like a final actually.
Yeah.
More.
It's just like a bunch.
So, I really didn't. I did okay. The final, because I didn't study. So don't be like me.
Oh, yeah,
That's what I got home from the party 4 in the morning. I took my chemistry exam. It had a headache, I couldn't even see straight.
right.
Yeah.
I like. Like.
It opens Monday, right?
Ethan, what's your major?
Biophysics. I'm gonna change because biophysics is looking on feet of the bunker.
Well, it's not boring, it's just hard in the part. I mean, like I spend all my days in the library studying.
Mathematics model.
So what are you changing? You think you're gonna go?
This class, I might do stats. You shouldn't though, just because my longer.
I guess.
Okay, right.
Do you know what you wanna do with it? Do you wanna go like teaching or?
Just do business.
GB test semester, that's just the right.
You go to something like 4 weeks. Wow. You don't know my story. Yeah.
Try the speed run.
That's the last one. I think maybe there's one more. Maybe. Yes. 25, yeah.
How equally weighted is the test between the stuff we just learned and the review of the test? You're like, 25.
So I think the study guide for as far as how many questions from each unit are gonna be on. I'm pretty sure for each point that has an X,
Okay, we're not.
there's gonna be 1 question.
Yeah.
So I'm not really sure on what the count is. I think there's more unit 2 and unit 4 than unit 1. Okay, so there's gonna be stuff involved. Okay, gonna give it the break. I'll kind of lose it easy. Ready to learn, get some knowledge.
There's no place I'd rather be on Thursday at 4:40.
There's no place I'd rather be. Yeah, that's sad, Okay, let's try to get this. So unit 3, we talked about kinetic. Well, we talked about gases. Mostly we talked about gases. And you guys did so awesome memorizing this, like, when we were going through chemistry, like everyone was able to just live this, and they knew kinetic molecular theory super well. So again, with this coming exam, I would memorize, not like super memorize, but be able to know the gist of these 5 points with kinetic molecular. Okay, basically this theory is just explaining the behavior of gases. If you know these 5 points, that's pretty well. That's good. Any questions? Okay. Talk about MRT, this is the ideal gas law. For this next exam or for the final, you should know the relationship between the variables. So you should know what happens when if one increases, what the other does. And a good tip is if they're on the same side of the equation, just like a direct. If it's on the opposite side, it's inverted. Maybe
I think it's the other way around.
it's the other way around. Okay, let me change. I'll change this out. Okay, 'cause I don't want to.
I found that one.
If it's on the same side of the equation, it's inverse change. But if you double the pressure, the volume is gonna be half. Like that's, if you double the pressure, I just said that.
Oh, yeah.
Don't think so.
When you double the amount of. Same side of the equation, you double the pressure, look at pressure volume, if you double the pressure, you have to have volume. So,
So I'm saying on the slide.
Yeah.
He just wrote it.
I wrote it wrong. So I'm gonna go through and change it. I did write it wrong. But let's look at this practice problem with your friends or by yourself. Just go through A to F. Come up with it, then we have the answer of the minutes. We'll do.
Yeah. you're-
Good about.
If
I just did take it.
It will.
Please, sincerely. I think I don't have any questions.
West Connecticut.
It's actually.
Yeah, by one.
Sincerely. Do you have any questions? Yeah.
Now cancel it too.
How the pressure of the gas be affected by falling signal?
It'd actually be the opposite.
That make the temperature less, not like a.
Volume.
I wouldn't call the winner, it just.
9 times.
So it's gonna be 13 by half. Not good. It's basketball.
9 times.
Yeah.
Not good, half.
It's because
Oh, that was good.
it's a,
Yeah.
so it's like technically.
Right.
So reduce it by 9.
That, right. Sit it down. That's the day.
You know, that would be like.
How much do it? That's 60 by one.
Just make it, it's gonna be new. Yeah, and then
Now I
see
do
the
one nine.
temperature, that would reduce, but that's.
Yeah, that was 190. Sure. Be a good song. Right. Down to nothing. Well, I guess that's not really relation. Okay. This pressure. So. Good. Okay, let's look at A. What do you guys say for doubling the volume? Half. Pressure will decrease by half. Yes, very good. What about for B? What happens when we triple the number of moles? Pressure will triple. What happens to the pressure when we reduce the temperature? Pressure will decrease by 1/2. Makes sense. Right, so if they're on opposite sides of the equation, same thing happens to both. If they're on the same side, it's inverse. Okay, so I wrote it wrong. We're gonna change it. Does this make sense? Okay, then for D, if we double the volume and double the number of moles, they won't change the pressure. That makes sense. And for E, it's gonna reduce, pressure drops by a factor of 9. You don't really know, that's like the worst way to say it. What did you guys say?
9 times smaller.
It gets 9 times smaller, okay, I mean, I guess that's
I said
probably.
it's reduced by a factor of 9.
Yeah, so it increases by a factor of 12. Yeah, right, we got it. So you should know the ideal gas law, honestly, PV, NRT, as long as you know that, all these ideal gas law questions are pretty simple. Here's a practice question, it's not the hardest practice question, ready to go.
Okay.
Just use 8, just use 8. Just say it's about, what do you say it's about 40?
How much are you?
It's about 310. Like 310 about 1 atmosphere.
Well, it's okay, all right, we might have a 5 for.
I'm 5'11".
You're not 5.
Yeah, no.
Five, so it's really just five, shut up.
It's like 0.08.
It's really not even 33, no, it's 70.
What you got?
It's five, it's about.
That's
It's really just like 8 million. Are you six, are you 6'2"? That's my only precise. Oh, 8,000.
Everyone thinks they're tall. He's the type of guy to put 5'11" in the Tinder bio.
Shut up, I think I am 5'11". Okay. There's no way that you look the same height. True.
I'm
Not five, stand up.
I'm 5'11", you're
Who is 5'11"? Is it 5'11"?
This guy right here, this guy right here.
You're not 5'11".
That guy's 5'9".
Who knows the guy? He's 5'11". Well, Craig, I'm not 5'11". But you're not 5'11".
It's the hat, it's the hat.
Oh, no, I take my hat off at 5.
He's wearing it with the loose fit.
Alright, shut up. What did you guys get? Answer. Number of moles. How many number of moles?
Couple of gone.
0.19 and 7.
Yeah, 0.19. Even the six.
Oh, yeah.
That's sick.
I know I
Solid.
did wrong, because I did the wrong.
Okay, guys. Oh, I'm sorry, there's questions. Yeah.
I'm just wondering, there's different R values, how do you know when to use which one? There's the, I know we use 8.1 in a couple situations.
Yeah.
Great question. So what you're always gonna do is you're gonna look at the unit. Okay, so for this one, you're gonna use the 0.0820578, whatever it is. Because that is in liters, atmospheres, or mole Kelvin. And that makes sense with what we're doing. Now the other one is in joules per mole. So if we're dealing with energies, we're gonna use that other, but we're not. For this one, we're gonna do this. Great question, yeah.
Ever use the other one?
What's the third one?
Ever use per mile?
I don't know.
I didn't think so, but I just
I don't know
saw.
why you have it.
Yeah.
Yeah. Okay, any other questions? This is a really good reminder. Honestly, you're gonna get into the test and you're gonna forget what STP is, okay? STP, is at 233.15 Kelvin. Inner pressure is 1 atmosphere. And, the molar volume of any gas at STP is 22.25. You know this stuff, it's like, there's not gonna be a question saying, at STP, what is the inner pressure? But there are gonna be questions with STP in it. You can have them out, but it's just one of the things you have to.
So,
The next two things we talked about is, it's just taking this gas law and manipulating it to find different stuff besides what's already in the gas law. So this formula is the one for finding molar mass. And I could show you the derivation of how we got there, but it's just easier for you and easier for me. For you to memorize the formula. It's on the sheet?
Yeah.
Oh, I never got this on the sheet. You guys have this one on your sheet too? Yeah. You guys are spoiled. Let's talk about real gases and ideal gases. So the ideal gas law, PV equals nRT, that will make some assumptions. Okay, the assumptions that it makes are that the molecules of the gas take up the volume, and also that there's no intermolecular forces between the molecules. This just isn't true.
Factors, you understand?
So PV equals nRT don't work. We're dealing with real gases. We have a different equation, it's called the van der Waals equation. It's just this big one. I think it's also on your equation sheet. You should just know from this slide, just take away what A and what B correct. What they mean. Okay. Any questions? Okay, quick review of intermolecular forces. It looks like a lot. It's just like descriptions of all of them. The ones we have are London dispersion, meaning order of increasing strength. We have London dispersion, dipole. We've got hydrogen bond, and we've got ionic. Okay, so ionic's the strongest, London dispersion is the weakest. Here's some little facts about all of them.
Yeah.
Yeah, any questions about this? I mean, we did intermolecular forces pretty recently, so it should be good. Maybe, I don't know. If you need a review, we can review. Any questions?
Here's this little chart I wrote, helped me. This one helped me understand the things when there's like a polar and a non-polar, or like an ion. You know what I mean? Like the ones that aren't dipole, ones that aren't ion, the other ones. So this is at the bottom, we did the topic of products. So, yeah, a little chart if you want to look at it. Okay, here's a little practice. I want you guys to go through and identify what the predominant intermolecular forces in all of those molecules are. Okay. So the intermolecular force that is the strongest.
CH3 dominant. There is
Is the second one? It's like a long chain. It's a long chain. The carbon hydrogen. With a huge net. Yeah. The second one is still on the upper side. Third one's like ionic. Example, okay, carbon oxygen bond.
I see, you know,
It's symmetrical. The next one. So we know that they'll have. Third one is ionic. Third one. Behind this big ionic. Idiot. This one is an H2O water. Hydrogen bond. This is the part.
Three dominant intermolecular forces, this first one. London dispersion, and that makes sense, right? There's no dipoles, there's no hydrogen bond anywhere. There's definitely no hydrogen. What's the next one? Dipole.
They're just
The oxygen on both sides with two methyl groups. The oxygen has two lone pairs on it. sp3 hybridized. Polar molecule, it's got a dipole. Maybe dipole. What about KF?
I still have like kind of.
It's ionic. What about this next one?
Hydrogen bond.
Hydrogen bond. And what about this next one?
Yeah. Oh, yeah.
Okay. What about this next one?
Ionic.
Ionic.
We totally get you mean.
Yeah.
Honestly, what's the point where like the size of the molecule gets large enough to where London dispersion overpowers like the hydrogen bond? In that middle one, how many more CH groups would we need before like
I think that's a great question. I'm not super sure of the answer. But on the test, you're not gonna have to buy it. Like it's not gonna ask you, it's gonna be cases where like one off.
Your score.
Yeah, but so should we assume that bonding is possible? That's the answer.
It's coming. I mean, I guess.
Yeah, because the CH3O, CH3.
Yeah, hydrogens.
That one can't hydrogen. So like.
Great. Any other questions? Any other forces or solid? Okay, the next thing we talked about was intermolecular forces and physical properties. So you just have to know the trends with each. So as intermolecular force increase, does boiling point increase or decrease? Increases. What about melting point? Increases. What about enthalpy of vaporization? Increases. What about enthalpy of fusion? What about vapor pressure? Decreases. What about volatility? Decreases. So vapor pressure and volatility are the only ones that as intermolecular forces increase, they decrease. So as long as you can know that, everything else is increase. Okay, does that make sense to everybody? Yes.
What's volatility?
Volatility. So let's say you have volatility is just how likely molecules in a liquid are likely to just escape and turn into gas, just at room temperature. So if you have H2O, the molecules of H2O, they're hydrogen bonding to each other. And so they're not super likely, even if another molecule comes up and smacks it really hard and into the surface, it's not super likely. If you have something like methanol, or I guess even methane, right? Super non-polar, there's almost no intermolecular forces at all. It can be super volatile.
any molecule that comes up from the bottom and hits a molecule on the surface, it's gonna smack that molecule into the air. Smack. Yeah, that's all. So yes, that's all. Okay, do you understand those trends? Yes. Yes, so when you have a sealed container. Oh, okay, what it falls like. So let's say this is water and it's sealed, and we have a lid here. Like so. Oh. Vapor pressure is the pressure of the vapor above the liquid. Yeah. And it really only applies when you're dealing with closed container, because when it's open, the vapor pressure is 1 atmosphere, right? Because the air is pushing down. Same dissolves like. Yeah. We understand? We all. Okay. Does that kind of answer your question? Yes. So, this is a good meme, but it's a meme that's truth. So that makes it even better. So your all reliable is therefore more energy is required to overcome the intermolecular. As intermolecular forces increase, it takes more energy to overcome them. That can pretty much be your endpoint for all of these, even vapor pressure and volatility. Except you should know the trend is reversed. Therefore, the volatility decreases as. Okay, we're good. Okay, now we get to unit 4. Okay, and this by a lot of people is what they think is the hardest. That's because there's a lot of math and the subjects are a little weird. Okay, we're gonna do a practice question. Hopefully, we all. So the first thing that you should be able to do, you should be able to do problems using stoichiometric equations. First of all, you should be able to balance. Okay, and here are some tips for balancing equations because it can be hard. And honestly, even if you practice a ton, it's still going to be not easy. Right? It's still kind of always a guess and check. Like practice will make it easier and help you understand what you're doing. It's never going to get to the point where you can look at it and go, well, that's a really easy one. You can look at it going, well, duh, this one. You know what I mean? So it's always kind of like process to do this out. Here's the tip. So hopefully help you. You can look at those out. We're not going to do a balancing equation in this way. But there are times online you can find. But the purpose of this slide is you should be able to, in a word problem, take amounts of one substance and use the stoichiometric equation, change it to the other substance, right? And that's just dimensional analysis, right? This on the side is an example problem that's been worked out for you. I wanted to ask you this question, but there's drawings on it everywhere. I couldn't figure out how to get those drawings out. The first thing I did was a balancing equation, and this one is an easy one to balance. Right? They have 2K on this side. This one is, they have 2Ks and 2 CLs. And they have just CL on this one. You're like, okay, well, 2. And that balances all the Ks and the CLs. They have O3 here. You have 2 O3s. You're gonna have 3 O2s. Right? That one's an easy one to balance. Okay. But using that, they were able to do a word problem. They changed the grams of KCl3 using this ratio to grams of O2. Okay. And that's what you should be able to do. You should be able to do something. Which honestly isn't that hard. And you've been doing it on your recitation and all that. Okay, percent yield. The formula for percent yield is just actual over theoretical. And we're going to do a practice problem right now. And this one's going to take a little bit longer than other practice problems. So, you have a question, just raise your hand, I can go over it. Hopefully there's a part B. I think this is a question that was on your recitation set. So, you could practice it. I can come up with I guess I don't know. Okay.
The weight of
See, so. Same number of moles. Same number of moles. We're gonna have that over 77.96. First one seen on the. Have X one. You're gonna use like a bow to get my sets. And the next one, you still have.
I'm so blind. Let's say each of us.
Yeah.
Need so much fun stuff. How much
So it told me that the actual, whatever, and it's only the year. It's an amount.
16 times 4.
Yeah,
That's everything. Grams of sulfur.
plus
98.
98.
I would get a grade higher than the total.
The number of.
But this SO4 is sulfuric acid. So we're gonna do 2 kilograms.
So,
Using dimensional analysis.
Wait, if you have it, if it goes to fixation. It's a 71.
Well, no, because the,
We have approximately 76 kilograms.
Sorry.
so you take sulfur,
The percentage will be the same. You'll,
and you add on a.
you know what, actually.
So that kilograms of acid, that is.
if I could just make a list of you. It would be-
Actually, that's still the same. It's one of those. Why? It's because you never times that by 3.
Have 1 mole.
Okay, you never times that by 1,000. You need all this stuff by 1,000. How many
Well, you wouldn't have divided it by,
You have to find the grams. You take it from grams.
76 kilograms.
Change it to moles.
Well,
that was 25 kilograms.
Yeah, man.
How many moles
Like,
does
these
it
math
have?
just took,
25,000 divided by 30
I don't know how to explain it. The answers.
times that by USO4.
How many more?
this ain't grams.
I did.
Yeah, divide that by 1,000.
Kilograms.
Oh,
You're right.
to ask-
Yeah, and I took 54 divided by that.
You're totally good.
Fun.
Oh, yeah, I'm chilling.
Having.
Awesome. I started.
You have to do it on.
Pretty bad.
You have a decision when you.
It's not bad. It's not always gonna.
No.
Chemistry. I don't wanna
You understand the process.
And the third one.
I don't know.
Bad.
You doing Spanish tomorrow?
You know that you have.
Yeah.
10 a.m.
I have problems.
Alex, I'm doing religion as well.
Gave me.
Probably wait for the finally ballot.
Look at my bio.
All the
What?
Don't have history. It's like scheduled for Saturday.
You got 71-1.
You have a role. I told Morgan. It's not a role. I go to chemistry. Saturday afternoon, maybe. And then like Sunday, live in. It's like, I don't have to worry about it.
Actually.
So I was right.
And then just next week,
I said he got 71. You got 71.1. You got 71.0.
See, my problem is I'm like, I would. If I just-
Problem by 0.02%.
And now I'm just-
Oh.
I could have been like, you know,
We get that, yeah, I know it's.
so that's like my trade off.
Yeah.
Okay, stop stress.
Well, yeah, 100%.
It'll depend on how I feel.
I have not.
This one is.
I've heard that.
If you don't text, go text.
My favorite.
You like-
The. It's like Jeff time.
Put it. I think it's good.
Take
Well, try to say 10 is like pretty good on, like. I don't know. Last year didn't have many grants. Not like a good, yeah, but it was. There's some other, like, remember the pump station I use? It's like it doesn't take it like it's just this problem. Like air comes, stuff like this problem. Said that number they gave you.
Yeah.
Like the bomb calorimeter.
Yeah, it's
Just being so.
what values like.
It's gonna be the mass of H2S.
Yeah, we have a starting value.
Yeah.
Same number.
This many more, and then now I'm gonna divide that to mean that. My next.
Make the second reaction.
Okay, how do we feel about RNA?
Awesome.
Awesome. Awesome.
Like.
Who's feeling awesome on this problem? We're all feeling good? What about part B? Part B looks harder, but it's always simple. So if you can do A, you can do B. How many of you know that percent yield equals actual over theoretical? So let's go to the next slide where we'll see some answers. So I think the first one is the answer for A. Okay, did everyone get this number for H2SO4? Did everyone understand the steps of how we got there?
Yep.
Everybody go through it or kind of forget it? Okay, the next one for part B, all we do is we take the, it gives us a, so it gives us an actual here. So we take this actual and we divide it by our answer in particle. And that should give us our percent yield. We get 71.1% yield. Does that make sense how we did that? Yes. Is there any questions? Okay, let's move on. The next thing we want to talk about is combustion analysis. This one can be tricky, but it's pretty. So this is just the first one is just combustion analysis. We take something, throw it in a container, and throw it in lots of and then our products, CO2 and H2O, is our products that we're going to be burning. That's gonna help us determine the empirical of whatever we burn. This is when we don't know what we're burning. When we don't know the formula. So yeah, and you guys know the difference between empirical formula and what's the other one? What's the difference? Yeah. So this is a little rhyme that the other TAs came up with for the process of combustion. It's percent of mass of moles divided by small. It's not like the best poem, but it's like a little thing. Like when you're stressed and like worried, like kind of all anxious in the testing center, and you're forgetting everything. As long as you know this, you can do. Oh, I mean, that's probably not. But I think the best way to learn is to practice. So here's another practice. I think this one was also on your recitation process. So at the end here, I kind of just where I'm. So, is everyone working on it? Are we confused? Is there confusion? No, we're solid. Is everyone done?
Okay,
Separate.
Green. Is 1, 2, 3.
You're right. Yeah.
Well, a milligram is 1,000 now, so you multiply it, you divide it by 1,000, that's 3, and you get 1, 2, 3. How many? How many milligrams, so assuming that you.
Oh, yeah, I did, because there's one trick with simple.
Yeah, who needs more time? Yeah, I'll give you like a minute more. You did multiply.
Now, like everything's gonna.
Zero. You're the mass of the carbon.
Maybe you drink, so if you do grams divided by per mole, then you have, just have, you know, figure out how many moles of CO2 you have, which that's,
C is gonna go.
that's 0.0103 divided by,
Have the same moles.
divided by, 44.
I'll play it during the next match.
Wait, you always said you were movie.
I haven't actually put my mind. I just forgot to play.
AMU CO2.
No, you times it by
Play them at the end. Grams divided by.
That's how many
Okay.
minutes I have to time.
This next slide should have the answers. Are we ready for the answers?
Oh.
Yes.
How many grams of CO2?
Yeah, I'll give you like 10 more seconds.
Just how much?
Okay, just don't look at the board.
How many moles of CO2?
So this was the first step, I think.
No, once you have.
Okay. So this is what we did. What was the first part of the percents and mass? So the first thing that they did was they took the percents, get the mass. Okay, does that make sense?
Percent of what? You mean by percent? So.
Yeah, I don't know. That's not my rhyme. So I don't know. That's not a what?
They usually give you.
Yeah, I guess they usually give it to you in percent. It's not really a percent this time, but they took this CO2, the mass of the CO2, and they found the mass of how many of the carbon in that CO2. That's the first thing they did. And the second thing they did was they took that mass, they changed it to mole. We have like 2 point something times 10 to the negative 4 carbon, and they did that many moles of hydrogen. Did we understand how we found the hydrogen? No. So the products of combustion analysis are always CO2 and H2O. Okay. The amount of C in CO2 is always the amount of C we had in our reactant. The amount of H in H2O is always the amount of H's we have. So, since we know that naphthalene or whatever this weird figure out that we were doing with only had carbon and hydrogen, what we can do is we can find the grams of hydrogen. If we take the mass of the sample, so I think the mass of the sample is like 130, something like that.
Molecular weight.
Oh, okay. So we took the mass of the reactant, so 3 times 10 to the negative 30 grams. We subtracted the mass of the carbon, and that's the mass of the hydrogen. Okay. This question was a little weird, but we understand how we did that. Thank you. Do we have it? Solid, maybe. It was solid 6 out of 10. Okay. What about mass to mole? What about all the other parts? The other parts make sense. The other parts make sense to everyone. Okay. So
Why do they multiply all the subscripts by 3? Multiply by 4, so like you can't have. And then why?
they're multiplying it by 2 because they're trying to find this second to last one. They're taking the empirical parameter. They're finding the empirical parameter. This one they're trying to find the. What they did here is they found the molar mass of this empirical formula,
Yeah.
and they found it was only half of
what it needed to be the molecular formula, because we had the molecular mass of 150. This was like 65. So we multiplied it by 2 to get the actual molecular mass. Okay, we solid on combustion analysis. If you're still kind of confused, you can go back, find the lecture. There's a video. You got it though. It's also on the practice exam. Okay, the next thing we're gonna talk about is endothermic versus exothermic reactions. I think we all kind of understand endothermic versus exothermic. Endothermic, it takes in energy. Exothermic, it releases energy. Up here, these are energy diagrams. This top one, is this exothermic or endothermic? Exothermic, right? Because it's starting here. This is the transition state, and then it ends up here. The overall energy of the system is lower. The released energy, the change in energy is negative. There we understand that. This one is endothermic, because it took energy, right? It had an increase in energy to the system. Endothermic. That makes sense to everyone? These signs make sense? Yeah, mostly. Okay. Okay. So honestly, this section is confusing just because there's a lot of way to calculate C. Right? And we know the formula that energy equals Q plus W, something like that, right? And a lot of times we're going to want to calculate Q. There's a lot of different situations where we're going to use different formulas to find Q. Okay. Sometimes we're going to use MCAT. Sometimes we're going to use, when we're doing calorimetry, we're going to use this CCAL. Sometimes we're going to use this Q and delta H, where the delta H is vaporization or fusion. Sometimes we're going to use the delta H of reaction. It just depends on the situation we're doing. But looking at this, you can kind of read and get a feel for that. Right? Does that kind of make sense? Yes. Sorry.
So we know that there are two different types of ends. Like we talked about with one end, the normal limiting reactant divided by stoichiometric coefficient. Is that just for the potential energy due to a chemical reaction?
When you're doing like bonds, products minus reactants.
No. So,
N is the other, N is the coefficient, the equation. Which one's which?
yeah,
Is that what you're asking?
yeah. Like there's one end where it's to divide by the coefficient. The equation.
So the one that you're thinking of, the one where you multiply by the right? Because this is the delta H of the reaction. We take the stoichiometric of the reaction of the thing we're looking at. So I would just know these four. Know when to apply each. I think one of your presentation problem sets had some really good practice problems. We were able to use all of these. I would just go through that again. Honestly, because it just takes practice. Yeah.
Most of these are on the sheet. The equation sheet, or you know these.
I think the MCAT is on the equation sheet. Is the MCAT on the equation sheet?
Yeah.
Are any of the others on the equation sheet? Yeah, you're just gonna have to know them. Sorry, guys, but no. Okay. So let's do the practice. So here it is. Here's a practice problem. So a lot of this practice problem is going to be figuring out which Q to use where, right? Because I'll just let you guys do it. Just go for it. If you have questions, raise your hand.
Specific key to price war. Specific key or
I guess you need that. All right, let's write that in. Yeah.
Well, I guess we're supposed to be, that's what we're solving.
Wait,
Oh, she's, you're right. Same thing like. That's like, it's like, there's like. States. So two different values technically, the specific key is what you put into the refining enthalpy change. The amount of energy produced. Well, you're gonna need to do that phase change, we need to know how much of that we're gonna have in order to find the total. For example, so that's why it's like just per mole.
I know.
But the other one is like the amount of.
Only the specific heat.
But that's functionally the capacity of steam. It's like, this is slightly different. It's slightly different. It all depends on the equation. 184.
biology.
The other one's gonna go.
First, you're cooling it down. You know,
Just like.
so it's MCAT is.
The boiling point,
So that.
100?
Yeah, it's not
200 divided by
first, it's the count.
Yeah, because.
No, it's 100 degrees Celsius.
No, I just know.
No, but like for the. Right, it doesn't matter. Trying to fix it.
And
It's 11.1.
11.11 volts.
Yeah. Fusion, vaporization.
Negative 40.
6, 7.
Yeah, and then vaporization. Yeah.
Five. Water.
change, is that just? And. That's it.
That's what we
Is
sit
it?
down.
Yeah, 100 to 0.
Plus changing temperature or something. Reliant on mass.
Times.
Yeah.
Well, it is.
Negative 6.0.
Um,
Remember, those are gonna be.
That'd be
Oh,
200.
you need to change.
50.
Calculate what's in.
Right.
So just go over
Your
to
first bit of energy. Second bit of energy.
Like add all these suckers, like.
Changing, you're gonna give the emphasis. It's like.
6.01.
I will join you.
Names.
Age, yeah.
You know what? It just gives you a number.
Wait, did you say it was?
You already did.
For the.
So once you have that, you have that.
Stage vaporization.
100. So it
11.1.
Treating your phase change.
it's 200.
Find us. So the sign for that would be.
And then you have.
That would mean.
They're gonna be negative.
Have the
That won't be.
ancient energy from.
Wait, number?
Vaporization. Vaporization is when.
Just again. Times 40.7. Times.
Changes there.
Fusion is changing,
You have 50 times 200.
I think so, cause it's in endo. Yeah.
Well, how does that make?
fusion is from melting.
The values won't be negative.
I don't know why it's called fusion. It was backwards, but.
But they're giving.
They're given as negative.
Yeah, it's not there.
So.
Did you do
There should be three.
Because fusion is when this enthalpy of fusion negative is when actually.
They're not taking it because you said it out loud. I vaporization, but it doesn't matter because both. And both are just the unit Saturday, the unit change, so it doesn't.
All these changes are now. We're gonna change that to
Saturday night.
Is that process?
Nothing?
Record.
Have them Mario Kart.
Kilojoules per
Spaghetti. Eat the spaghetti.
piece of pretty similar.
Kind of wants to.
Oh, for real?
Yeah, you go into the movie.
It takes.
My dad works in it.
Cause I made those.
It'll take.
Does not know it. Because instead of melting,
Take that out. The opposite. So it's exothermic when ice changes.
station.
I think either way, it does have to be negative always. The amount of heat.
I was gonna
say, that
sounds probably.
There's no, that's either the balance.
at the end, you could change the.
Or you have to change it though, because a lot of times, what way is it going? It gives us so little time. If it's the same no matter what.
Makes sense, it would take down a lot of energy.
We'll see what he says.
Yeah.
So we can either.
You might be right.
Because, I mean, would they all be negative?
So I just remember these problems and I never changed those.
Because technically they're exothermic.
I can really do that.
They're all exothermic, endothermic.
And with the temperature, just going down. He is. It should be positive. I like positive.
Thing about the season. We'll see what the final is, because I'm confused too.
Put it like.
You like.
Because I.
Let's see, you got, see.
I got 640. Decimal, character now.
Boys.
You say that.
Then 20 kilojoules, you're chilling. If you wanna bet that there are at least 10 questions, or they're just the same thing, like it's for the same answers, and they're not the same thing.
You gotta do that units. Okay, guys, this is a long question, but who's ready for the answer? Are we ready? We all ready for the answer? Okay,
So,
we're able to get it. This is what you do.
It's negative.
So let's look at the first thing. The first thing we have to do is we found what
You're on it.
Actually, no, you were both.
Right? For changing phase, we need to make the number of moles. Vaporization. So negative. Number. The problem with negative number is the answer. Kilojoules. You have to make sure you change the joules, the kilojoules, or the kilojoules to joules. Make sure all your units are the same. Is this the answer that people got?
Yeah, because
We feel solid.
LP is given negative. In temperatures.
That's good. Proud. Okay. Any questions? Yes.
So with the like delta H of fusion and the delta H of vaporization, we wouldn't have to like change those signs if we're going backwards, like from steam to.
yeah, I was about to ask the same thing. Wouldn't the Q for N delta H be a positive result because it's a negative of a negative value?
Honestly, so they did negative there just to change the sign, but you would have to do positive. Because the enthalpy of vaporization is when water turns into steam. This is the value for when water turns into steam. Okay, so we're turning steam into water, we have to flip this around and make it positive. Same thing with this thing, yeah.
But then wouldn't that make the Q of, sorry, the Q of fusion positive then at the end, mathematically? Or I'm saying like if we're doing like delta H is normally negative, right? And we're flipping a sign, so it's a positive times a positive, right?
Yeah, I know.
I mean, I guess. So I guess.
I didn't need to give it negative. Let me turn it on.
We got a negative.
Oh, that's really soon.
But isn't the equation positive?
Yeah, we're still.
Why is the negative?
Set to for the negative side.
I'm not really sure. I don't know. I guess now, The negative number, going from steam to ice, if it's ice to water, it's a positive number. I don't know, I'm not sure. Oops.
The right ones on the test, right? Like. we
They
won't-
will give you the right ones on the test. Yes.
That equation is always cute.
Why is that one cute?
Is it positive?
They just made it a negative.
Equal and delta A.
Yes.
It's an exothermic.
Yeah. I can-
I think it would make sense to change out the signs to wall, because it have to be a fusion of vaporization, or you would change the sign on.
Heat of vaporization would have to be
Make
Positive.
because you have to add energy to break.
Yes.
Yeah.
Oh, okay, that makes sense.
Totally, and that's what we all, or that's what me and the people we were talking, I was talking to thought. They were just confused why we did a negative. Right here, right here.
The Chem.
Yeah.
That makes sense.
Like,
Yeah, that,
Okay.
yeah. So, I don't.
You just need everything to have the same sign, and it's like, yeah, those are written in negative values, those are written in. Single values, you're gonna do both sides.
I would honestly look at look at the notes, again, look at the PowerPoint, go through details one on the PowerPoint. So I would go look at that, maybe she has more words for why it is the way it is. If you're still confused, I would go look at, just some online videos. I'm sure I know they have good stuff like this on. Go look at that. Let's talk about calorimetry next. Calorimetry is a different kind of heating and cooling, a different way to find the enthalpy. And it seems complicated, it's really not. We just have to remember that because of the first law of thermodynamics, all the Q's added to zero. So we get that one Q equal to negative. Right, makes sense what I'm talking about. Okay. So at the bottom here, this is just a little flow chart to help you to know which one to use when you're doing what. So if we go through. And you're given a problem, and you don't know which of these two equations to use. You can kind of in your mind go through this. Is it heating up or is it changing phase? What's happening? If it's changing phase, give me potential energy, you're gonna go down here. And if it's phase changing to this, it's going to react to this one. If it's just it's heating up, it's moving down, changing the back area into this one. At the bottom, however, we'll actually talk about now, this one. So I would do this chart, I'm gonna know when to use what. Any questions? This is Hess's law. So we did Hess's law. These are the rules. So when you have the formulas, the mini baby formulas and the big formula. If you need to swap, reverse one of the baby formulas, or the one under, then you're going to reverse the sign of enthalpy. Okay. If you're doubling the coefficients on one of the baby equations, you can double the other. Does that make sense? So this is a practice question. It shouldn't be too hard. I tried to get a not too hard one. You guys want to do this practice a question?
7 halves.
Do it.
Let's do it. Okay, do it. It shouldn't be too hard.
oh, we don't.
Solve it, Alex. We are at 4,712 just means 71,200. That's actually, because it's not G for gas, G for, gravity, there's not an element, it's just G. Basically what the reaction is saying is that, it's not a reaction between. That's just what happens when you. When you put the other H2H6 into a particle accelerator. Accelerate it at 7 to gravities. It turns into CO2, it's 3H2O.
I think so. Yeah. And the extra O2 is just, they just come. I mean, the oxygen smash the carbons together.
Yeah, it's just the energy from the speed.
Yeah.
That makes sense. I think it makes sense.
That's all part of logic.
Solve it. Anyway, there's an extra on page 2.
Really, James.
That would make sense. Bombs would be
CO2, yeah.
without that.
When it is that, we can do products manager.
Plus 30.
Yeah.
Yeah.
Yeah, what is?
You're gonna just add this one.
You have that extra.
Okay.
That's good.
Here's the answer.
Why?
Don't worry.
You got it.
Okay, and this makes sense. Right, does it make sense to everybody? Not as bad as it looks. Actually, one of the easier things that you do.
We're gonna talk about.
So, yeah. Okay. Moving on.
What's the thing?
We're on slide 75 of 82. We're almost done with it. And we're gonna push through. So the next topic we're gonna talk about is making fuel choices. Okay, so you guys will be given a table, most likely you'll be given a table with lots of fuel. It's gonna ask you which fuel is bad. What you're gonna do is you're gonna change all of the fuel, all of the energy values that you're given into a fuel value. And that is just the energy released during combustion of 1 gram of sodium. Okay, so all the values they give you is gonna be a kilojoule per mole. You're gonna change those values to kilojoule per gram. Compare them. And that's how you put your answer. So here is a little break. We can't do this practice, bro. I forgot to put I'm just gonna put the answers. Okay, yeah.
It's okay because we should always just use the renewable fuels, right?
Yeah. We didn't even burn it.
So true.
Okay, so here's the answers. I forgot to give you the so that's my bad. So let's talk through this. So what we did was for each of these fuels, it gave us an value, an energy value of when we burned it. So for hydrogen, it gave us this. And honestly, if you don't know what to do, we'd be like, well, this one's the biggest, so it has to be the best fuel. But what you want to do is you're going to change these into moles using the molar mass. You change it into kilojoules per gram. We compare them all. This one has the highest. Well, I guess. Yes. Good question.
Okay, so I know on some of the application stuff, they'll like give us like a name, like ethane, ethanol, we need to know what the practices are.
You can fit more. No, not.
Those aren't gonna be.
But you can fit more. That's something they're not like.
I know that.
I mean, you can have it's just if there are less kilojoules per that probably means thing is
Yeah,
smaller.
so
Sweet ram feels too more efficient.
Yes.
We're gonna have to memorize the formulas for the fuel they'll be given to us.
So someone just asked that, and honestly, I mean, they didn't give you the here. Representation problem sets are a little different, whereas they like kind of expect you to use Google sometimes. I don't think so. They must. Right, and I mean. That would be one carbon. So it's CH4. This one is just 2 carbon with just hydrogens. So it's just carbon with hydrogen. Or I mean, ethanol is that ethanol is
It feels like midnight.
2 carbons and instead of 6 hydrogens, there's 5 hydrogens. I don't think you are. I don't think there are. But maybe. I haven't looked at the text, so I don't know, but I'm pretty sure they wouldn't like do that. Or just wouldn't be like, they'd be testing your knowledge of random formulas, like it's not really. But probably. You know what I mean?
Question is just natural.
But do we understand how we do this problem?
I just heard.
Let's convert it into kilojoules. Put your hand, one is the biggest, that's your fuel, right? Okay.
It's something bigger.
Let's talk about changes in entropy. So we should be able to look at the reaction and tell if the entropy is increasing or decreasing. Okay, so in the things that affect entropy are states of matter, number of free particles and complexity. I mean, it's pretty intuitive. For A, is the entropy increasing or decreasing? Increasing, right? Because it's turning a liquid into a gas. So the molecules have a lot more room to move around. What about for the part A? What about for the second part A? Increasing or decreasing? Increasing? It is increasing. Why is it increasing?
More particles.
More particles. What about for the third part A? Decreasing. Wow.
Fewer particles.
Two particles. We're going from 7 to 2. It's like a lot less.
Like 20.
Yeah.
Yeah, literally.
I mean, like, maybe it's other ten of them. So like, if the other things were the same, is it like losing and more complex stuff in the molecule that has more entropy?
Yeah, I think so.
Oh, thank you.
Yeah, very good. Yeah. Does all make sense to everybody, the changes in entropy? This one's simple. What you're gonna wanna do is you're gonna want to take this and apply it to like word problems. But let's talk about signs of enthalpy, entropy, and free energy. Okay, so a lot of times this can be confusing. There was a chart that she gave us, which is super helpful. It was just included in her start. But if heat is being released from the reaction, and the delta is the same, right? If it's exothermic, delta is the same. The heat is being absorbed, the delta is positive. Okay. If the heat is increasing, heat is absorbed. For entropy is immediate. If entropy increases, change entropy is positive. If it decreases, change entropy is negative. For free energy, if it's exothermic, it's the same as enthalpy, where exothermic will delta G will be negative. If endothermic, delta G will be positive. Okay. This one was easy, but the next one is kind of like a question. So.
Oh, that's right. Yeah, they left.
Like, that's.
Wait, are we looking at A or B? A. Can you solve the answer?
It's one, these are sublime. It's source.
Negative. That's all right.
Part B.
And so entropy is also.
So honestly,
Right, and so negatives, the negatives will cancel out, so entropy is working against us. It's typo. Depends on the small. I think at night is assuming those.
I don't remember, Alex, there was like something about like.
No.
Where I don't,
Same negative.
yeah, that's just not standard.
The temperature is high enough. Is there change in? Yeah, that's how the change. It just happens. You can. If I do. Delta, no, that's not negative, that unless it's biased, right? Like.
The signs for part A.
Negative.
Tell me, what is the sign of delta H? What's the sign?
Negative.
Negative. What is the sign of delta S?
Negative.
What is the sign of delta G?
Negative.
So negative. Understand why, right? Okay, what about the part B? And this one, it should be cancelled by in the gas. This was from your recitation problem set. It was wrong. So it's wrong here. But I put the line into gas.
Solids.
This one because it happens spontaneously.
So if that changes your answer. For part B, what is the sign of delta X? Positive, right? Because it's changing the gas from solid to gas. What is the sign of delta H? Positive?
Positive.
Yeah, delta H is positive also. What about delta G?
Negative.
Negative, why is it negative?
Spontaneous.
Spontaneous. If delta G is negative, it is spontaneous. If delta G is positive, reaction is not spontaneous. The reverse reaction is spontaneous. Okay. Does anyone have questions about these problems? Yes.
This is all assuming high room temperature. right?
Temperature is given, so yes, but also there's nothing assumed.
Okay, if we're not given a temperature, do we assume room temperature?
I think you'll always be given the temperature. Yeah. If there's not a temperature,
I don't think temperature will really matter.
yeah, if there's not a temperature, but it's saying that something's happening, then I think you could still figure out. Yeah.
At that point, you just assume delta G is negative, but it's spontaneous because it's happening.
Thank you.
So she gave you this chart. This is a super helpful chart. You should know what signs do what. When it's always spontaneous, when it's never spontaneous, when it's spontaneous at high temperature, it's at low temperature, it's so hot. And this is using that equation that we had, delta G equals delta H minus T delta F. Solid? This is kind of like accumulation of everything we've done so far. So this is like the last practice problem I'll have you guys do, and then we're done. Okay, so we're trying to find gives free energy, and I'll give the answer in a little bit. Okay, ready, take a look.
What we're gonna do.
What is the what are the products and what are the reactants? What products and reactants? Yeah, what's the conversion?
They write it on the board. Sorry.
CO2.
What happens to the
PPO.
chemicals? When the chemicals no, which chemicals start out? From the past.
I'm in irrelevant CO2.
Yeah,
That's the only way you have things that the chemicals can do.
that would make sense.
And these chemicals are in the past. But never in the-
True. That's true. Yeah, I guess it doesn't have to be endothermic way.
I'm in an elephant.
Okay, guys, I'm gonna write it on the board.
That's true, Chase, man.
Sure, though.
I think it's just 1 mole of each.
Sure is a shoe.
Yeah.
Well, all the air out there.
That's broken osteoris.
What's the composition?
This is right.
I'm gonna take Saturday.
What's it?
Here's your reaction. Sorry, I didn't have that on there.
And then this is where you use Hess's law thing. You just do. I don't slot it. Technically.
Yeah, no.
Your amount.
Apparently, I was thinking.
That would be, about 600.
I didn't have all your notes, as long as you want, look stuff up on.
Yeah.
600
minus 7. Except it's negative.
For the other. It's all.
It's like girl though.
Not true.
The 10, 90s, approximately 6.
Why? Are you gonna be an
Negative 700.
So,
Connected those numbers.
6 foot, I don't think you're 5'10".
Minus react. This is like one over 5 times.
Post, math ain't math.
Yes, you're.
What type of guy to put 5'11" in this reactor? Just put 5'11".
Figure out what you're doing.
Yeah. Stoop that low. Desperate.
So, how long?
Turn 23.
Like 270.
That's the point.
50.
Oh my God, what's your 23rd birthday?
Already solved it.
We got time.
Got time.
Maybe by the time you're.
That is not right. When you skip a mistake, that'd be 50.
Uncle, met you.
If they do that.
Only at work. My cousin did it.
Okay, are you guys ready for the answer on this one? So this one is, what you're gonna do is you're gonna find, first you're gonna use all the formulas you've learned so far. The first formula you're gonna use is the formula for delta H. Right? It's gonna be products minus reactants, I think, right? Yeah, you're just gonna use products minus reactants, delta H. You're gonna use, for delta S, it's also products minus reactants. And for delta G, you're gonna use delta G equals delta H minus T delta S. Okay, something that you had to do for this one was change the 325 degrees Celsius into Kelvin. Because entropy is a unit of joules per mole. So, just gotta make sure you watch those units. Any questions about how we did this? Oh, yeah, go ahead.
Like delta something, it's products minus reactants. I remember the one instance with reactants minus products, but I don't remember what the.
For bonds.
Bonds, but it. Yeah.
Yeah, that was bonds broken, but the bonds formed. So, yeah. Great, yeah. Okay, we have like 20 more slides to do. I'm just kidding. Good luck. Hopefully not that bad. So good luck. Study hard.
Isn't this the test you bombed? Isn't this the test you bombed?
Isn't this the test you bombed?
Isn't this the test you bombed?
Oh, yeah. Well, okay, but listen, I didn't listen, I didn't study.
Ethan, don't worry, it's easy.
What'd you get on like?
I got home for like 4 in the morning.
Knows. He knows, don't worry.
I got hundreds on all the midterms.
You bombed this one. Really, this one's so much harder.
I took it at 4 in the morning for a party. Just don't be like me.
That means I'm gonna get it out.
I'm not trying to be discriminating.
Yeah.
Don't take the 5-10. I've been listening to me clearly, but going to
I just want to put these were so helpful.
You did it slow. I still only hear it.
Like 5 minutes.
Wasn't expecting you to make it 5.
You guys a little bit more.
This was like by far the most like productive.
Going
Yeah.
to actually mistake.
Oh, it's like in the group chat.